There are assumptions in mining that things can't change. Even though it may be slow and expensive, we do things a particular way because it works. The risk is that this thinking can blind us to new things when they come our way.
Let me tell you about a game-changing update to electromagnetic exploration technology, CTAC's Mineral Finder technology.
Mineral Finder technology is being accepted in the Middle East, USA and South America, by miners and investors to reduce risk in exploring tenements. The old industry model for exploration is to take a long time and carry a big upfront cost to explore, drill, value the asset, then move to production. The Mineral Finder technology goal is to turn that model around. So, with Mineral Finder technology upfront you can quickly, and for low cost, quantify, map, and value the asset. Then you spend a lot less time and money to execute a small number of highly targeted confirmation drill holes, after which you can finance the move to production. So, let's talk about some of the challenges of exploration, and then I can outline how MFT addresses them. Long exploration cycles. Mineral, gas, and oil exploration is a set of processes that are followed to discover whether economic resources occur in a particular area. The process generally begins with broad-scale exploration over a wide region, for example, regional datasets and remote satellite sensing. As targets are identified, study narrows down, thorough investigation of geology remotely, then in the field, with surface and stream sediment sampling, to produce geological surface mapping. It finishes with shallow and bedrock drill core sampling. The project may start looking at prospects over a 100,000 square kilometer range, and with each phase, the delineation reduces by 2 orders of magnitude, until it typically ends, looking at several targets, in a 10 square kilometer, or smaller, area. At the end of each of the various exploration steps, there is a decision to progress, or not, to the next stage, which is determined by the results of the previous stage. The exploration process usually takes 3 to 5 years to complete. Spiraling exploration costs. With dwindling resources and relatively low accuracy, two-dimensional, surface-only information, from traditional remote sensing, significant drilling is required. Environmental compliance regulations are also increasing in complexity and lifting exploration costs. By the time exploration is complete, up to $250 million may have been invested on the drilling phase. Dwindling resources and high risk. The field of risk management has been developed to a high degree in the oil and gas industry. However, in the minerals industry, progress has been slower. With the dwindling number and quality of mineral resources, mineral exploration requires high investment, sustained cash inflow, and considerable time, with inherent high risk, where risk is defined as chance of failure or loss. The current average success rate is only 5%. 20 potential sites may be explored, at high cost, to bring one ore body to production. Environment. Mining inevitably disturbs the environment. Equipment access roads, subsurface examination through drilling, and trenching, causes environmental impact. Drilling can take a direct toll on local water sources, biologic life, and natural resources. Impacts from drilling can also be indirect and unintentional. The complicated nature of drilling techniques, in unstable areas, means the impact can't always be accurately predicted. That's where MFT comes in. As one mining client described it, MFT is an MRI for ore bodies, a non-invasive environmentally friendly technology that yields accurate 3-dimensional ore body maps quickly and for long. How does MFT address those challenges? Shorter exploration cycles. One of the biggest benefits of MFT technology is the speed. The MFT process is very fast compared to the traditional remote sensing and on-ground sequence. It can cut 4 years off the exploration phase. With MFT, Phase 1 spectroscopy, data processing, and analysis takes up to 6 weeks. Should you proceed with Phase 2, then on-site work, with a team of 6, takes 6 weeks more, for 12 weeks in total. MFT leads to very targeted drilling, in other words, a requirement for less drilling, so shorter drill periods can accelerate the move to operation and profit. The quick MFT process leads to shorter exploration cycles, so you can evaluate more potential sites. Cost. The next benefit is cost reduction. The average accuracy MFT historical data, developed by comparing MFT three-dimensional ore body maps with drill cores, is 94%. There is no other passive technology that can give you this level of detail and accuracy. The result from this accuracy is less drilling cores, high drilling success, and a reduction of up to 80% in drilling capex costs. The low cost of MFT and reduced cost for exploration also means you can evaluate more potential sites. Risk reduction. Exploration involves economic risk and uncertainty. Risk reduction can be addressed in 3 fundamental ways. 1. Increasing the number of examinations. 2. Increasing success probabilities, and 3. Changing success probabilities per test, by learning. MFT can address these factors by, for example, reducing the time and cost to assess, so more examinations can be conducted. And by improving the accuracy of assessments, thereby increasing the success probabilities. Environmentally friendly. MFT uses passive sensing to discover mineralization potential. It has zero impact on the environment. I'll talk about the physics principles behind the technology at a high level. Ore bodies, in the subsoil and bedrock, create electromagnetic anomalies in the Earth's magnetic field. With the right equipment, these anomalies can be detected passively and measured, quite precisely, to give indication for where to investigate further. Traditional satellite imagery and spectrometry, using radio waves, microwave, and infrared light, produces surface pictures, produces imagery of the surface mineralization, but not the subsoil. But surface presence is typically not more than 50% of the total ore body, so surface imagery contributes to low exploration success. What makes MFT unique is that, in every phase, it produces data that is not surface pictures, is not imagery, it is subsoil geophysics. Built from the processing of multispectral information from satellite, remote, and ground-based detection. While MFT also uses microwaves, the focus of MFT is the deep blue and ultraviolet spectrometry and resonant frequencies of minerals of interest. MFT proprietary database has data on the resonant frequency of every mineral and ore of interest. The UV resonant frequencies used are not from academic research, nor in published literature. And if MFT have a mineral sample, a drill core, we can precisely calibrate the resonant frequencies of the polymetallic materials of interest in your ore body. Most metals are too reactive to exist on their own in the earth, and they exist combined with other elements. So, ore bodies are highly variable in nature, appearing as native elements, carbonates, sulfides, oxides, hydroxides, etc., and as happened with one client, there were 6 different forms of copper in the one ore body. But MFT is able to delineate between them. There is no other passive technology that can give you the 3-dimensional level of detail and accuracy and polymetallic differentiation you get with MFT. MFT helps resource companies doing exploration to verify the minimum number of points to be drilled to qualify an ore body. MFT uses a mix of deep blue, through ultraviolet wavelength, satellite spectroscopy, short pulse electromagnetic fields, vertical electro-resonance, AI and manual data interpretation, to map ore bodies, up to 10 kilometers deep, with accuracy averaging 94%. MFT is a 2-phase process. Phase 1 involves analysis of remote sensory data. MFT takes satellite spectroscopy data and processes it to identify areas of subsurface mineralization and the concentration of ore in those areas. Phase 2 involves field sensing at greater levels of precision of the areas of most interest identified in Phase 1. Phase 2 involves 2 steps. The first step, uses FSPEF, typically done from air, land, or water vehicles, to develop more accurate maps of the subsoil mineralization and grades. The second step employs VERS to develop maps of the depth and thickness of the intervals containing the minerals of interest. The final output is the combined spectrographic FSPEF and VERS data to give accurate three-dimensional maps of the below-surface deposits, assessment of the mineralization grade, volume, and value. The maps are used to direct targeted drilling and minimize the subsequent drilling required to certify an asset. So, let's have a look, in a little more detail, at how it works in each phase and each step. The first thing that is important, in Phase 1, is the scale. That is, the distance between each point of control. Each point where we have information. We start Phase 1 with sample points, at between 10 meters and 200 meters apart, and sample areas, ranging from 5 square kilometers to 100 square kilometers, depending upon the input material. As we move through Phase 2 and Phase 3, the spacing between measurement points, or scale, becomes less and less, with accompanying increases in accuracy of the map. For example, if the area examined by spectroscopy was 5 square kilometers, that is 5 million square meters, and resolution, or measurement point spacing, was 10 meters, that is 1 point per 100 square meters start speech, end speech, then the spectroscopy data will have 50,000 sample points. We analyze the spectrographic data to produce a matrix of the subsurface ore bodies. Then, we run that data through software that produces isolines. It joins the points with the same electromagnetic resonance frequency as the resonant responses of the material we are studying. Normally at this phase, the report doesn't give you the precise shape, nor multiple layers, of the mineralization. It will tell you if the mineral is there, whether it is 300 meters or 3 kilometers below the surface, and if it is worthy of further analysis. When looking at oil and gas, we track up to 10 resonant frequencies. When it is ore bodies, it can be between 3 and 6 frequencies, and then we build a map that is a mesh of them all. This example chart is the case of a greenfield chromite ore body in Colombia. What you are seeing is the result of the Phase 1 geophysics process that gives us a first-pass map of the subsoil areas where we detect the frequency of resonance of the ore of interest. The purple areas are subsoil chromite deposits. The orange area is copper and silver. Observe the darker colored ore bodies. At the top center and bottom center, the darker coloring is showing us there is more mineralization in these areas. This example chart is the case of a copper mine in Chile. This one was brownfield. There were 6 different types of copper here, and we found type 1, 3 and 6, in concentration in the tailings. And this represented significant value that was being overlooked, and was subsequently processed. There have been other cases where the tailings were important. For example, a Colombian client who was mining gold. MFT, Phase 1, showed rhodium was present in both the ore body and the tailings. And so, the mine started processing for the rhodium too. This is why the technology is also very good for brownfield exploration. There are 2 steps in Phase 2. First, the FSPEF, for more accurate mapping of the location of mineralization, and second VERS for accurate depth mapping of the ore body. In Phase 2 Step 1, the FSPEF step, we know, from Phase 1, the ore body anomalies are there, and where they are. So, we limit and focus our further investigation to the subset of anomalies of most interest, to improve resolution. The selection of which to investigate is made in conjunction with our client. In Phase 2, Step 1, we crisscross the anomalies with GPS and small portable FSPEF units. Our equipment issues a short impulse at the frequency of resonance of the material of interest in the anomaly. The pulse interacts with the anomaly, if the material of interest is there. And it generates a response which we capture and process. At this point the resolution is increased, or if you prefer, the scale is decreased, by an order of magnitude. So, if spectroscopy points were 100 meters apart, the FSPEF will be 10 meters apart, or if the spectroscopy resolution was 10 meters, it will be an FSPEF measurement each 1 meter. Remember, from my earlier example, the spectroscopy data could have 50,000 data points. If the anomalies of interest made up 20% of that area, and so 10,000 data points of interest, then after FSPEF we'd be processing and meshing 10,000 spectroscopy and 100,000 FSPEF data points. The mode of transport can be air, horse, car, foot or boat. And the crisscross can be in any direction, which is important, because on the ground, movement is often limited by the topography. In this example, the ore is gold, and the country is Mexico. The client instructed MFT to only show the veins more than 60 centimeters wide, and ignore the rest, because it would not be economic to mine the smaller ones, initially. You can see in this image, a spectroscopy map, which is the red boundary lines, overlaid on the gray contour lines, of a topographic map. You see the 3 anomalies of interest, from the spectroscopy analysis. The mineralized zones are those bounded by the red lines, making the 3 banana shapes. The large one in the center, and the 2 smaller ones, to the left. The area bounded by the yellow line, and shaded with yellow diagonal lines, is the zone of metastatic alterations. The actual veins of the mineral bodies, identified from the FSPEF, that are thicker than 60 centimeters, are the bold vertical red lines, inside the 3 larger red boundaries. No other passive technology can do this. Now you can see exactly where to drill for certification, and so you can avoid the irrelevant 80% to 90% of the area identified by spectroscopy alone. This saves a lot of elapsed time and drilling expense. You will only take core samples where you know you will get results. Another advantage after Phase 2 is the increased accuracy. In our experience, satellite spectroscopy can have spatial errors of up to 50 meters because, for example, the satellite is moving, and the Earth is moving. This is not precise enough to direct drilling. Remember, you also get the matrix of data points, with specific measurement detail for each point, not just the surface visual representation. In this example, again, the ore is gold, and the country is Mexico. You can see in this image a spectroscopy map, the purple boundary lines, overlaid on the blue contour lines, of a topographic map. The yellow, and orange, is the overlay of the more detailed FSPEF results. What is worth noting, in this example, is the top right of the image, where you see 3 areas of mineralization, Oro 11, Oro 12, and Oro 14, identified by spectroscopy, and bounded by purple lines. Spectroscopy identified some big anomalies, but most of the areas had low mineral concentration, and were not economic to mine. However, the highest concentration areas, worth drilling, and mining, were 150 meters outside the areas identified by spectroscopy alone. Only using spectroscopy would have led to drilling in the wrong place, and exploration may not have discovered the profitable areas of the deposit. The same applies for Oro 10, in the top left. In Phase 2, Step 2, we use vertical electro-resonance sounding, VERS, for the depth dimension mapping of the ore body. Some people describe it as virtual drilling. In the VERS step, we focus our further investigation to the subset of anomalies of most interest, identified after the previous steps, to improve resolution and understand the depth of the reefs and thicknesses of the ore bodies. The selection of which areas to investigate is made in conjunction with our client. In Phase 2 Step 2 we crisscross the anomalies with GPS and small portable VERS units on foot. Antennae are inserted into probing points that are usually selected in the central parts of the anomalies. The VERS equipment issues a short impulse at the frequency of resonance of the material in the anomaly. The pulse interacts with all the subsoil layers, down to 9.7 kilometers, and if the material of interest, the one at the resonant frequency, is there, it generates a response, which we capture and process to create a vertical layer mapping. We also identify groundwater in this step. After this phase, we will have built an accurate three-dimensional map of the ore body and the grades, so it is possible to make preliminary calculations on the volume, mass, and value of the mineralization. At this point, the resolution can be increased, or if you prefer the scale decreased, by another order of magnitude. So, if spectroscopy points were 100 meters apart, and FSPEF were 10 meters apart, VERS measurements can be made 1 meter apart, depending on the client requirements. The mode of transport here must be on foot because the equipment is inserted into or in contact with the earth. We can crisscross the ore body in any direction where ground movement is limited by the topography. In this example, again, the ore is gold, and the country is Mexico. Here you can see an example of the VERS measurement at one data point. It reports mineral concentrations at 20 meters, 5 meters thick, 60 meters, 1 meter thick, and 120 meters, 3 meters thick. We collect data, like that in the previous slide, at every sample point, at spacing of between 1 meter and 10 meters, and then interpolate the data, so we can build an accurate map, like this example, showing the vertical arrangement of the gold veins, tectonic faults, and groundwater. When you are planning to drill, you now know where to drill, what angle to drill, and how many sample holes you will need to certify the ore body. This can cut the drilling back to 20% of the normal number of cores, and cuts drilling cost accordingly. MFT employs unique software and algorithms. These process the ore body data that comes from the ore samples and 3 different electromagnetic sources. MFT uses a mix of supervised and unsupervised deep learning algorithms that are based on multi-layered neural networks. These are effective for pattern recognition, anomaly detection, and feature extraction. The MFT algorithm and modeling contrasts with the traditional methods. Conventional methods for resource models require a great deal of subjective manual interpretation and estimation, using whichever method generates the least error. The accuracy has always been dependent on the skills, efficiency, and subjectivity of the operator. And the process is very slow. The MFT neural network deep learning approach can rapidly generate classified and domained ore body models. These include the estimation of multiple numeric variables and uncertainties directly from the ore sample data and spatially referenced pre-coded survey data. This is the future of ore body modeling. So, let me tell you the story behind the images here. The ore body contained gold, silver, and copper, and the country was Mexico. The client had spent $10 million on previous geophysical field work, and, since then, there had been 5 years without progress on delimiting the deposit. They invested $1.5 million on an MFT survey conducted over an 8.6 square kilometers study area. The study examined 27 gold anomalies and was completed over 12 weeks. MFT reported 1 million ounces of gold reserves. The gold alone was valued at $1.5 billion. As a result, the mine was valued at between $150 million and $250 million. Shortly thereafter, the drilling results verified the MFT accuracy at 94%. And confirmed the certified concentration and value of the gold, copper, and silver mineralization. MFT has been used successfully by many mining clients around the world, in the Americas, Africa, Europe, and Asia, to reduce exploration time and cut drilling costs. The slide shows a small subset of client names. You can, I think, now appreciate that MFT responds well to some of the key challenges of greenfield and brownfield exploration. Taking only 12 weeks to develop an accurate 3-dimensional map of a resource body, MFT helps significantly reduce the typical 5-year exploration cycles. Because it provides ore body maps with average 94% accuracy, it can reduce drilling cost and time by up to 80%, significantly reducing the hundreds of millions usually spent on drilling. With dwindling resources and more complex locations, by reducing the time spent in, and resources deployed to the field, MFT can also significantly reduce risk. What does one invest in an MFT project? To explore 5 square kilometers with MFT, the investment is around $1.3 million. Typically Phase 1 is around 60% of the budget, and Phase 2 is around 40%. There are alternate options that are results-based, where you can pay, over time, a percentage of the drilling costs saved over the following years. One MFT client, after testing the technology across several greenfield exploration projects, became so confident in the reliability, accuracy, and speed of the MFT technology that they changed their business model from long-cycle operating mines to short-cycle buying tenements, exploring them with MFT and minimal drilling, then selling the certified reserve for a profit. If you'd like more information, contact us using the details shown.